Hey everyone, and welcome to another episode of TRX Bench. Today I want to follow up some questions you dropped me, and it is all about how to connect a Spectrumanalyser to a device under test. And well, some of you seems to think it is a kind of secret how a Spectrumanalyser get connected to, in our case, radio. But it is not. It is fairly simple, but it really looks like that some of you are struggling a little bit with how to, and therefore let's talk a little bit about how to manage to connect a Spectrumanalyser, but not only a Spectrumanalyser, as well a frequency counter or a deviation meter, right, to a radio. And I mean, you all know, and that is where the question is coming from, that you really can't directly connect a radio with let me say 100 watt output directly to a Spectrumanalyser, because you really would blow the front end, because a Spectrumanalyser is a very sensitive device, and therefore you really need to take care, and therefore let's look a little bit into that, and I promise it is really not a secret, and it is not rocket science. So let's go into that. Okay, so let's simply go right into the video. So here on the bench, this is here my bench radio, which I use for driving, amplifiers or what have we. So the only purpose is to have something to produce power for testing devices, whatever. Right. So let's take this radio to demonstrate what we are talking about. And this radio is set to AM, so that we have a carrier, because the carrier is, yeah, let me call it, which is carrying the power, right? And so we use AM to have this carrier. Let's see how it works out. And then you see me using here my Spectrumanalyser, my signal Hound, and well, I'm pressing here the transmission or transmitter, the PTT switch, whatever you want to call it, like so, and we see here a carrier. So in our case you can already see it, because I have here my marker on the top of the carrier, and you see it is yeah, almost 10 dBm, plus 10 dBm. And well, that already is an interesting point. Why? I will show you. You see the radio in transmit, and here this pot here is my power, my drive potentiometer, where I can set the output power. And you know, this is closed, completely closed, right? And if we would watch our power meter on this position, you see this, right? And why I'm telling you this? You see no power, right? Again, I go down here, and I do it without switching off the camera. So still here our pot is really completely counterclockwise, so no power, and that is exactly what our power meter is reporting, okay? But on the other hand, you see here our carrier on our Spectrumanalyser with 10 dBm, okay? So that might already give you an impression how sensitive this device is. So we do not see nothing on our power meter, but we already see a carrier on our spectrum analyzer. And still the same setting. Now I go and crank up here my power pot clockwise, and you see while I'm increasing it here, you see 100 watt, right, on AM. So that is another story. So that's a wrong setting in my radio, but completely different story. So you see 100 watt output power on the power meter, right? And now back counterclockwise, 0. And now let's watch both instruments. So I do exactly the same. I'm cranking up here my power meter, and you see on the LP100 that I'm increasing here our power, and you see that our carrier on our spectrum analyzer is going up, and you see that the spectrum analyzer is reporting 50 dBm, and you see that the LP100 is reporting 100 watt. So maybe you see a second very important information. While I'm cranking up here the power, watch our spectrum here and see what the power meter is showing us. And you see, while I'm cranking up here very little on the power meter, our spectrum analyzer carrier is going up much faster. So see how heavily it is going up, while we only have 1.1 watt here on our LP100, and you see that it is going more slowly when we are getting up here to 100 watt. And that is exactly telling how logarithmic calculation works out. So this on the LP100 is linear. So you really see our power going up in a linear way, right from 0 up to 100 watt. And it is different on our spectrum analyzer simply due to the fact that it is in a logarithmic way, okay? Alright, and you already may wonder, so why do we have it here in dBm, so in decibel, and here in watt? Why simply do we have it here not also in watts, and why do we have it in dBm? So I personally prefer to have it in dBm, in dB, because it is so easy to calculate, and you really can add it, you can subtract it, so you can do everything with dB simply in your head. So you do not think about how many volts is this or that, and yeah, you reduce it about that, and how many watt is it now or so. In dB it is always very simple, and therefore I personally like to use dBm, right? And dBm here in our radio world is all calculated on 50 ohm, because our load resistor, so our antenna, is or should always be 50 watt, and the 50 ohm, and the output of our transceiver or of our amplifier always should be 50 ohm, okay? And therefore dBm is always calculated on 50 ohm, so all is around our load resistor or our source resistor, okay? Okay, but you may already ask, hey, what is the setup? How do we take here simply, you know, a coax cable like we have it here, and I simply connect it here to the spectrum analyzer, and then we have here our carrier. So how is it possible? So you told us that you know, we really need to be careful not to connect the radio directly to a spectrum analyzer, because a spectrum analyzer is very sensitive, and you are putting it here directly to the input of our spectrum analyzer. So how gets it together? Okay, let's look behind the scene. Okay, so let's look here where it all starts. So the radio is simply connected here to my coax cable, and now how does it work out? So we go here behind it, and now you can see it. This here is my dummy load, so that is a 600 watt dummy load, right? 50 ohm, of course, and you see here my LP500 sensor, which is of course connected here to the dummy load, and therefore of course we can read the power on our LP500 display. But then there's another little information, and right down there you see a second connector, here connected to our dummy load. So you see here the input, and here down there behind all the wires we have a second connector, and that is the testing port. So that means we take a portion here of our signal right out of our test output, and with this test output we really can test it on the spectrum analyzer, and I tell you how it hangs together. Okay, but what have we seen? So when I'm pressing here PTT on the radio, we see that our carrier is at 50 point something dBm, and as long or since 50 dBm is 100 watt, because that is what we have seen on our LP 500. So you can see it here, 100 watt is equal to 50 dBm. Okay, so that means we see 50 dBm here on our screen. So how is it possible? As long I have told you that the spectrum analyzer can't really get connected completely to the spectrum analyzer. I take the power down because here my radio starts switching on the vent, and therefore let's reduce it a little bit, that the radio does not have work too hard with all the power dissipation and such. So okay, so how is it then possible that we read here 50 dBm when it is forbidden to connect directly the radio to our analyzer? And that is very simple. I already told you the second port at our dummy load is a testing port, and this testing port is reducing our signal with 40 dB, right? So it is not longer 50 dBm at the test port, but it is 40 dB lower. So that means it is then only 10 dB. And then I have a second little attenuator right here at the input, and this is another 10 dB, right? So that means altogether we have 50 dB attenuator in between. And that means if I'm putting in 50 dBm, which means 100 watt, okay? It means that the Spectrumanalyser input only sees 0 dBm, and 0 dBm is something what an analyzer can simply handle without any problems. And now you may already recognize how easy it is to work with DBM or dB in general, because as I told you, 50 dBm input, and I have an attenuator, the big dummy load with 40 dB attenuator, and then here our little attenuator. So we have 40 dB and we have 10 dB, which is together 50 dB. And now when I put in 50 dBm minus 50 dB minus 50 dB attenuator means simply we have here a power level at our Spectrumanalyser of 0 dBm. Okay, so you see how easy it is to calculate with dBm, because you only have to add it and then you can subtract it, and very easy to handle. And well, but why do we still see here on the analyzer screen, I mean when I crank it up here, okay, to 100 watt, why, you see it here, why do I read 50 dBm? That's very simple. Look here at this figure. Come on, focus. There you can see it. So we have a reference offset of 50 dB. So that means our spectrum analyzer takes our attenuators already into account, and the spectrum analyzer knows by this reference offset that there is an attenuator in between, and therefore the analyzer is able to calculate the right power which is putting out by the radio, and that is a kind of beauty. But what we can do, so we can of course take this correction factor out, and now it is I have to take it to 0. Alright, now we put it to 0, and let me do it this way. So nothing else what I've done. So let me see, yeah, let me put here both meters in the field of view. Okay, now our correction factor is set to 0, and now let me transmit again. And what you can see now, you see here our 100 watt output power. But now if you see here our carrier, you see here our 0, and when I go now to peak, you can see now our marker is on peak, and you see here our analyzer is now reporting 0 dBm, and that is of course right, because now you can go along and do again exactly the same. 50 dBm input minus 40 plus 10 dB attenuator is 0, and our analyzer is reporting exactly the right value. That is very easy. So you always have to calculate your attenuator, so you know you need to know what your radio is capable to put out, and then you can calculate to value what your analyzer or any device is able to manage. So how do we know what the device, your test equipment, is able to handle? Very easy. So this is front panel of our signal Hound, and what you easily can see, and that is a very, very important information. So you can see it here. Our spectrum analyzer is only able to handle plus 20 dBm max. You never should shoot above the maximum rated input power, because then you definitely will damage your spectrum analyzer or your frequency counter or your deviation meter. It is always the same story. You need to know what you expect from radio, and you have to calculate your attenuators that you can simply drive here your analyzer input. And here on the front there is a second very important information. Here this signal Hound, you see, is not able to handle any DC voltage, right? This analyzer is designed to display from 1 Hertz up to 4.4 gigahertz, I believe. But if you want to go down to 1 Hertz, right, you really have a device which is not able to handle any DC. So therefore, the first device here in front of my spectrum analyzer is a DC block. The DC blocker, you know, works from 500 kilohertz upwards. So that is really nice. 500 kilohertz is just fine, because we use very seldom signals which are below 500 kilohertz. Okay, but my second analyzer, so let me go over to my second analyzer. And of course you have probably seen me working with this analyzer as well. And if we go down here to the input information, you see here this analyzer is able to handle maximum plus 25 dBm, and this analyzer is able to handle plus minus 50 volt DC. But you see that this analyzer is starting at 9 kilohertz, and that is simply due to the fact that there is a capacitor in between which is blocking our DC. And I have it on the signal Hound externally, and here it is internally, and you pay it with that you only can start from 9 kilohertz, and if I want, I can use my signal Hound from 1 hertz. So that is all to the blocking capacitor in between. Okay, so let's summarize a little bit what we have done so far. So we have first here our radio, so that means our transmitter, okay, and the transmitter is of course connected to a dummy load, and the dummy load of course has 50 ohm, because the output of our radios always have 50 ohm as well. So that is how it works. Okay, so that is here the basic configuration when you work with a dummy load. This dummy load here is able to handle 600 watt key down. Okay, if you wanna, or if you need more power, you need of course a different dummy load or a different attenuation. And what we have learned, so of course what we have here is a kind of black box, which is this here. All right, in our black box we have here our input connector, and then we have seen an output connector, right? And the output connector is our minus 40 dB test port. So whatever you put in here into our dummy load or into our attenuator, you always get a portion of the signal here out of our test port, and it is always 40 dB down. Then we have here our wiring, and we have here our connector, and we have seen I connected here a second attenuator minus 10 dB, and then we have connected here our radio to the Spectrumanalyser. Okay, and that is basically the configuration how we did it. And again, now it is very easy to calculate when we have here our 50 dBm, which is equal to 100 watt output power, right? Then 50 dBm output power minus 40 plus 10, that means we have 0 dBm here at the input of our Spectrumanalyser. And we have seen that the Spectrumanalyser is able to manage plus 20 dBm, and that means with 0 dBm you are always on the safe side. Nothing what can be destroyed in your Spectrumanalyser with a configuration like this. Okay, so that means you always need to know what power you are expecting that you can calculate with your attenuators. And as we already said, our 100 watt, because that is maybe for you a more known value. So the radio is putting out 100 watt, and we know that this is 50 dBm. Okay, but now you may already wonder, how do we know? Let's say we have a radio which is putting out 30 watt. I mean, okay, we know 30 watt is below 100 watt, so that means that this configuration may work. So you do not really think about this configuration if you go below 10 watt. But maybe you are working with a different attenuator, and this here is through attenuator as well. And let me see if the labeling is gone. But anyways, this here is able to handle 100 watt power, and it is no, here we have it. There is a labeling. All right, so you see this is handling 100 watt, and this one is attenuating by 10 dB, and it works up to 2.4 gigahertz, right? So you know, if you have only this here, so maybe you want to think about if it would work with your analyzer. Can you put this here in between with only 10 watt to feed 30 watt out of your radio, and then you want to connect this end here to the spectrum analyzer. Does it work? Okay, so let's see how you can check it out. I mean, 30 watt. The first question is now, how can we convert it to DBM? I mean, I have to admit, the easiest way is finally to work with a chart like this here. So you have all the DBM values, and you can convert it from DBM to watt to volt RMS to volt peak. So all the different values for all the different instruments you are using. You can use, of course, this kind of tables. But I mean, let's do it here by hand, because it is fairly not so difficult. So we only have one formula, and the formula, as we are working here with power, we use our DBM, right, is equal to 10 log P by P ref. Okay, so that here is our formula, and that is really not very complicated, because as I already said, we are here in our 50 ohm system, and we are calculating everything to 0 dBm, and 0 dBm, which is our reference value, means 1 milliwatt. So 0 dBm is equal to 1 milliwatt, again in our 50 ohm system. Okay, so that means that our power reference value is 1 milliwatt, and the only thing you need to do is put your figures into this formula. And now let's see how it works out. Okay, we are looking for the DBM value for 30 watt radio output. We want to know the DBM value. Why do we know? Why do we want to know it? Because we have here attenuator, and we know that our spectrum analyzer is able to handle 20 dBm, and is 30 watt too much power to use this attenuator to feed our spectrum analyzer? So that is the question. Alright, so we simply put now our figures into our formula, and that is, as I said, very easy. So we say 10, and we use our logarithms button here, and now we put in our figures, because we said 30 watt, which I put here on the top, and we said that our reference value is always 1 milliwatt, and milliwatt is -3. Okay, and now we can go and calculate it. And what do we see? 30 watt means 44 dBm, right? If you have a radio which is putting out 30 watt, means you have 44 dBm. And now it is easy again. So 44 watt minus, again, where are our values? 10 dB means we have 34 watt, which will be at the output of our through attenuator, and that means 34 dBm is too high for our spectrum analyzer input. Since we know that the spectrum analyzer, hey focus, what's going on here? Since we know that our spectrum analyzer is only able to handle 20 dBm. That is how simple it is. So now you know that it is not possible to only use this here to handle you 44 dBm output power, which is equal to 30 watt power. Okay, let's double check it here with our table, just to verify that it is right what we have done. And you see we have here output power, and here we have our dBm value, and we said we want to look for 30 watt. And well, yeah, it is a little bit different here because we do not really have all the different watt levels, so we go close here to our 30 watt, and our table is telling or showing us 33 watt, and you see here that 33 watt is 45 dBm. And now we can already, or we can check it if here our table is telling us the true. So let's simply do exactly here the same, okay, with 32 watt. And again we put it here in, so our logarithms, and then we put in our 32 watt, you see it up there, and again to our reference value, which is 1 milliwatt. Alright, and we want to know what is here the result, and here it is. So it is really 45 watt and 45 dBm. So that means our table seems to be right. 32, 45. And that is a way how you can convert it always, your watt, your power level to a dBm level. I mean, if you do not know exactly what the radio, what you're using, is putting out, so you simply connect it over your dummy load to a watt meter, a power meter, and there you may see, oh, my radio puts out 32 watt, and then you go and calculate your 32 watt into a dBm, and you see, oh, it is 45 dBm. Our 32 watt is 45 dBm, and that means that here our attenuator, which is attenuating by 10, is not able to reduce our level to a value which our spectrum analyzer is able to manage, and that is the whole story. So basically very, very easy, and it is exactly the same with our frequency counter and with our divation meter. Let's have a look on our devices that we know what are the values over there. Okay, so our spectrum analyzer is telling us that you should never exceed, here you can read it, 5 volt RMS. So that is really the maximum value. As long we know that our 0 dBm, so we have calculated once again 50 dBm output, right? Reduced by 40 plus 10 is 50 dBm attenuator. So 50 minus 50 is 0. So our input power will be 0 dBm. And that means that we can simply feed in a signal with 0 dBm here into our counter. And let's do it, because it is exactly the same. So I take again here our input, and I connect it here to the input of the counter, and I know that we have 0 dBm at the input. And now when I'm pressing here my output power, you see that we have here now our transmission frequency. Radio is set to 28.6, and you see that we have here 28.59914. So it is a little bit out of frequency, but I mean the counter is not completely heated up, so therefore there might be a little error, and of course the radio is not 100% on frequency. But anyways, here we only talk about the levels we can put into our test devices. The beauty here of our table is fairly simple. So you see 0 dBm means that our RMS level is 224 millivolt. So that means we are putting into our counter 224 millivolt, and that is really a safe level which our counter is easily able to manage. So the only thing what you need to have in consideration is that there is somewhere a sensitivity question, and the sensitivity questions means that you cannot reduce the level at the input to your counter down to, I don't know, minus 70 dBm, because then the level is too small that the counter is able to report the frequency. So I do not completely have it on mind what the sensitivity level of my Racal Dana is, but it is about minus 30 dBm, I believe, and that means with 0 dBm input level you are on the safe side from the sensitivity point of view, and of course from the input level point of view. So both needs to be in a certain range, and with 0 dBm or plus 10 dBm, whatever, you are always fine. And we have exactly the same here with our, let me see if I can make it a bit better. Yeah, maybe. So we can see it here on our deviation meter as well. So the maximum input level here is 3 volt RMS max, but that is not your operation level. So you have two inputs. One is normally set to 1 volt RMS, and this is set to, or configured, so configured might be the better term, to 100 millivolt. So I mean, it depends what the signal is, what you are working with. So therefore you have two inputs. What you already see, it is the same. You can't put your 100 watt output power to your deviation meter or to your counter. It is exactly the same question. So the best way is always to go over your radio output power, what you have tested with your power meter. Then you know it is maybe 32 watt. That is the maximum output power, and then you know, okay, 32 watt is 45 dBm. Now I can calculate my attenuators in between, and I know where it ends up. Maybe here in this case, if it is 45 dBm, so that means reduced by 50 dBm, so you are at minus 5 dBm, right? So 45 dBm minus 50 dB attenuator minus 5 dBm. And so that is always the way how you need to calculate your levels, and that is what you really always have to do. So when you are not sure what can be connected to your test device, you always should go this way here to be sure that nothing goes wrong. Okay, so here you see we have no dBm value as we have it on our spectrum analyzer, and you may wonder how to convert here our input voltage to dBm, or the other question is, how can I convert a power level, I mean 100 watt for instance, to a volt level in our 50 ohm system. Okay, that is a little bit more advanced. It is not so complicated, so I will show it to you. But for all of you who are not so firm in mass, just look out for one of these conversion tables on the internet, so you can search it on Google, and it is available in the internet. And for all of you who want to calculate it, it is quite simple. So we have calculated here to our power reference of 1 milliwatt, but we know that 0 dBm is 1 milliwatt, but also 222 millivolt, right? And to be able not to go over our 1 volt or 100 millivolt, which is shown here on the deviation meter as maximum input, you should be able to convert it to the volt level in our 50 ohm system. And well, it is basically the same formula. When we calculating with volt, we only need to use 20 instead of 10 when we are calculating in watt. All right, and to convert it, if you ask how can I convert my 100 watt output power, our 50 dBm output power, in voltage within our 50 ohm system, so that is always very important, then it is quite simple. Since power is this formula, you can convert it to volt, and so this is the formula to convert finally a power level into volt within our 50 ohm system. And let's do it here on our calculator, then you may see that it is really simple. So we want to know what 100 watt is in volt in our 50 ohm system. And therefore let's here take our square root, okay, and we know that we have 100 watt output power out of our transmitter, and we know that we are transmitting into 50 ohm. So therefore we multiply it here with 50 ohm, and we just want to know what is the voltage, and we put it here on our equal button, and you see our output voltage is 7.7 volt. So now we have here our third figure, and that is 100 watt is equal to 77 volt. And we always, it is a very good practice to write, you know, here always the dimension in which we are working here to our formula. And so this is now showing that 100 watt is 70.7 volt in 50 ohm. And now we can do exactly the same. So we can calculate here our DBM level, or we can calculate finally the DBM level of a given input level. And you know, we have finally our input level here at our counter. So we had 5 volt, for instance, and now we could calculate it this back to DBM level. So let's do that. So that is what we are doing here. So we are converting our level of 5 volt, which is the maximum input to our counter. We convert it to DBM to calculate with our attenuators if we are able to reduce our level enough to have a safe level at the input of our meter. And therefore we say, okay, we have 5 volt maximum input level, right? And we use this formula now, and you see we have 5 volt and we have our reference, which is 0 dBm, which is equal to 224 millivolt, and that is what I have put here into our formula. And you see our 5 volt is equal to, yeah, let me say 27 dBm, which is quite high. And we know that when we transmit with 50 dBm, so that means with 100 watt, and we attenuate it by 50 dB, we have 0 dBm at the input, and the maximum rating is 20.97 or 27 dBm, which the front end of our counter is able to handle. And then we know that with 0 dBm we are totally safe, and we cannot blow our input of our counter. And that is exactly the same with our deviation meter. So in case of our deviation meter, we would put here 1 volt, and we would do here exactly the same mass to know what the maximum rating is here at the input of our deviation meter. And so well, you see how you really can manage it, and how you can control your levels to be safe. Well, I hope that all helped a little bit to understand how it hangs together. And again, this is here all maybe for the bit more advanced approach, but using here a table is not wrong. I'm using the table as well, because then I can easily you know, calculate all the values, that I do not overdrive the inputs of my instruments. And that is what I'm doing always. I'm very carefully with any level I put to an instrument, because the instruments here are my own, and I just want to use them in the future as well, and I do not want to get the input damaged by a wrong input level. So I'm really doing it anytime I'm working here with yeah, a radio or whatever we are testing here, that we are on the safe side. Alright, I guess that is really all I can tell you, and I hope you see how I'm doing it, and it is no rocket science. And if you always calculate with your dB values, which are printed on your Spectrumanalyser, which are printed on your attenuators, then you can always determine if you are in a safe area, in a safe window or not. And if you're not in a safe window, you should not transmit. That is how easy it is. Alright, I hope you all have successfully repairs, and hope this was of any help for you. And thank you for watching, and catch you next time. Bye!